Okay, hello everyone. Today we're going to talk about, we're going to wrap up our course on paper recycling, and what we're going to do is we're going to use all the tools that we've learned through the semester to understand how a total paper recycling system is designed and how it operates, the different parts. So let's get started. Okay, just as a brief introduction, we're going to look at a whole bunch of different things that are involved in designing and making the quality product that we need out of recycled paper. Okay, our learning objectives are, first thing we want to do is appreciate the strategies involved in designing a recycle process. So what are some of the key things that we think about when we're trying to understand how many unit operations we're going to have in there and what types of unit operations, how they're connected. It's like a puzzle. Then we're going to recognize the relative number of types of sub-operations in each type of recycling process. And then finally, we're going to try to understand the rejects, the sludge, and the water management systems in a recycling process, because these are really important for quality and for production. Okay, this is an analogy I like to make. If you would think of the paper recycling process as a plate, and I show that plate right in the middle, and that plate needs to be balanced, okay? So that we want that paper recycling process to be balanced, not fall over. Well, what are some of the things that can make that paper recycling process tip over? Well, the first three things that we need to consider are on the top of the plate, and you can think of them as weights. Production is important. We want to have a certain production rate so that we meet our goals. We want to have a certain yield. We don't want to be throwing away too much of our valuable material. And then finally, the quality of our product has to be such that our customer is happy and that we're happy. So we have those three kind of weights on the top of the plate, and you can see that if you move all three weights to one side, it's going to tip over. So if you move one weight, you might have to counterbalance it by another weight. So you can see that the quality can't just be moved anywhere on that plate because the yield, because the plate might tip over. So if you move to higher quality, you might have to lower your production or lower your yield. On the bottom of the plate are kind of the pedestals that are holding that plate up, and there are three that are very important: profit, safety, and environment. We've got to be we have to have a safe operation. That's number one. Nothing really matters if people get hurt. We have to have a profitable operation, so the profit has to be there. Without the profit, we'll go out of business. Our company will decide to shut us down. And then finally, the environmental issues. We cannot be harmful to the environment. So you see that safer operations will have to move that pedestal in a certain direction, or increase profit. We can try to make that our goal and move that in a different way. Or we might have to face some environmental challenges and change the balance of our recycling process by moving the environmental pedestal. So it's a pretty difficult act, and we've got to balance quite a few things. All right, now pertaining to that quality weight that we talked about, there's quality issues that are very important to our product that we sell. We basically sell our product because it has certain qualities. And we can kind of go over all the different kinds of qualities. We can break them up or categorize them based on white systems or brown systems. White systems are usually used for printing and writing grades, newsprint, copy paper, things like that. And the brown systems are basically packaging. And of course, in the brown systems, we've got a lot of unbleached kraft, which makes it brown. So basically, some of the product quality parameters that we're looking at, for the white system, we're looking for mainly optical properties. Strength is important, but optical properties are primary. We want to get high brightness, low dirt specs. We want to eliminate color or have a certain desired color. We need to get rid of stickies. Our customers don't like that. And our paper machines don't like that either. And then the ash content has to be controlled. So too much or too little ash is going to give us all kinds of different problems, such as strength properties or smoothness, things like that. Now for the brown system, we don't have as much issue with the optical properties. So we're more looking at just cleanliness, so that the box needs to perform, but it doesn't need to be that beautiful or optical. So really, and I think I left this out, the brown system, one of the product quality parameters that's most important is strength. And I have not put that on the table. So please note that strength is one of the #1 criteria for brown systems. Okay, if we're making like test liner board, we need to have certain tear and tensile strength and crush resistance, ring crush resistance, or stiffness. When we're making folding box board, stiffness is a very big issue. So one of the product quality parameters that's most important is strength, and I haven't put that there. But for cleanliness, it also needs to be clean. We need to protect our paper machine, first of all, or our board machine, and we also have to make sure that the cleanliness is such that our end user can use our product. So stickies are #1, foremost the enemy. That's going to deposit on our paper machine and cause us problems. So we really want to get rid of stickies. And the other issues are flakes, sand, fines, and ash content. Things like waxes can be considered stickies, and those are also an issue. So you see that in our brown system, the optical properties aren't as important, but strength and cleanliness still are. Okay, when we talk about process water management, in a white system, what we're interested in is we want to get rid of suspended and colloidal solids. Okay, and the reason why is because these usually contribute to the cationic demand right here. And that cationic demand is going to impact the way additives, things like sizing agents or strength enhancing agents, how these things interact with the fiber. So if we have too much suspended and colloidal solids, we will not have a efficient use of our additives. COD is important, chemical oxygen demand, because we're going to have to discharge some of this material, and that COD is a load on the receiving body that takes our water. Conductivity and pH are also important factors for bleaching or for the paper machine. We've got to control those. Now for brown systems, some of the same items. Suspended and colloidal solids are important, COD, cationic demand, conductivity, and biological activity is also important. Okay, I'm just kind of trying to go over some topics on this. So we talked about quality. What is quality issues? And we just mentioned they're different for white and brown grades. And now let me mention about yield. Here we go with yield, and I'll kind of help you out here with the graphic papers when we're making printing and writing grade. The yield might be between 75% and 90%. Okay, so we're going to have waste of about 20% in these systems. For the hygienic papers, the tissue paper, our yields are going to be a little bit lower, 28 to 40%. 28 to 40% rejects, and that the reason why is because we're going to want to get rid of filler material. That filler material interferes with our creping process. Market de-inked pulp, we're going to have, because we're selling market de-inked pulp, where people this is competing with virgin fiber, we're going to have to make it very clean and optically correct. So 32 to 40 is a reasonable percent by weight reject stream. And then liner and board, 4 to 9%. So for our brown grades, because our optical property issues are not as important, we don't have to throw away as much material, do our de-inking processes that have lower yields. Okay, and then finally that other weight on top of that plate was profit. And this graph kind of shows you, well, what kind of incoming furnish are we going to choose? You can see that the pricing can be very different, and that can have an important effect on your bottom line. So here we have sorted white ledger, and just at this peak here, we were at around $400 per ton. Imagine if you had a process that could either take sorted white ledger or mixed paper. Mixed paper being around $100 per ton at this peak. You could see that your profit margin might be much, much higher with the lower grade materials, so that's another issue. And you can see OCC and ONP are intermediate there. So depending on how strong your recycling process is, that should dictate to you how much of the lower cost material you can handle in your system, and that should help your profit. Okay, a lot of text here, but system design considerations, and I'll go over this just briefly. Like I said, there are many objectives of a recycling mill, and profitability, meeting product quality specifications, environmentally acceptable, and reliable and safe operations are all important. So we've got to consider all of those. All right, and then to do that, we've got several variables that we can adjust. So for instance, the incoming furnish type, the type and number of unit operations. Many times you go into a paper mill and you find that some of the unit operations are bypassed. Well, some type of decision has been made that states that the benefit did not outweigh the cost of using that unit operation. You can change the order of operations. So those are some of the variables that you can change. And then there are other variables that in a mill that are really uncontrollable, and you have to just deal with them as they come to you. And that's the price and availability of raw materials, the price that you're getting for your product, and then changing government regulations, environmental issues. So the bottom line here is that at least in the United States, we went through a real rough period in the 1990s where several dinking plants went out of business because they built the system on certain assumptions, and then when those assumptions proved to be invalid or constraints changed, they found it hard to make a profit. All right, so we can even go further on other system design considerations and talk about the raw material. Sometimes the raw material that you're planning on using may not be available, so you might have to spend more money to try to find that available material somewhere else or use a replacement material. The raw material can go up and down in cost, and you've got to think about how suitable that raw material is for your process. So if you have a process that doesn't have de-inking and you need de-inked pulp, you have to start off with a pre-consumer waste that has no ink in it, and that's going to be maybe expensive. And then the other thing about the raw material is the usable fiber content. If you're making tissue, it's very important to not purchase incoming paper based on tons total, but the tons of fiber total that are coming in. Some paper grades have 0% ash, and some paper grades have 30% ash. Tissue, you can't have ash in it. So you're going to have a very low yield if you buy cheap paper that has a lot of ash in it. Okay, you also have to think about the products that you desire. Are you looking for optical properties in white grades or strength properties in brown grades? For the optical properties in white grades, having a lot of short hardwood fibers in there is probably very reasonable. But having a lot of short hardwood fibers if you're trying to make test liner for strength is not good. So you've got to think about the fiber characteristics and how they're going to impact the desired quality product that you have. Environmental constraints. Depending on what mill you're at and what the conditions of that mill are, there might be a preference to have solid waste, or maybe a preference to have water effluents or gas effluents. And so each mill is going to have their own separate condition where they can decide which one's more important to them. Some mills have space requirements. You have a paper mill in a city, and there's certainly just a constraint on the footprint of your recycle mill. And that's very important because recycle mills need to store several days or weeks or sometimes even months of recovered paper so that the operations aren't interrupted. So space requirements can be an issue. And then, of course, you've got capital costs. Your capital costs dictate to you in the beginning of your the life of your mill, if you're going to turn a profit, your return on investment. And then operating costs can also be important, impacting your bottom line. Okay, so let's just kind of talk about some general process strategies we'll see in the design of some recycle mills. The first thing is the obvious. If there's a contaminant that your system can't handle, you've got to keep it out of the feed to your pulper. For instance, this can be done by making sure that the supplier of your recovered paper clearly understands what you can and cannot handle. And even if that does occur, there should be somebody at your mill when loading the pulper that's looking out for these unremovable contaminants and making sure they don't get into the system. In the pulper, we want to make sure, we talked about pulping, and we said that we want to detach the contaminants from the fibers. Without that detachment, our other unit operations are not going to work. We're also going to want to remove contaminants as early in the process as possible. So there are chances that contaminants can redeposit on fibers, get in our water system, and just kind of cause, or break down, actually, and make more dirt. So we want to get them out as soon as possible. Another general rule is instead of breaking contaminants, we'd like to keep them large, at least early in the process, so that we can enhance their removal. They're easier to remove if they're bigger. For some inefficient steps that are important to us, like flotation deinking, we will have to repeat those steps. And I put inefficient there, but sometimes they're not inefficient. It's just that's the limitation of the technology. So we'll have to repeat some unit operations to get maybe some cleanliness things that we need. And then we're going to try to save fiber by cascading unit operations. So we talked a lot about cleaning and screening and how we can cascade those to save fiber. And then we're going to avoid excessive changes in consistency. And I'll show you an example of this. We want to try to keep all our low consistency operations together, where we have a lot of water in there. And then when we need a thick, we'll have to invest in a thickening operation or washing operation if we need to do high consistency operations. Okay, so the next thing I want to talk about is the major recycling systems. And we can kind of generally categorize these from the materials, the products that we're making. First category is packaging materials, the brown grades, for instance. And typically OCC materials are used to make liner board, medium, and tube stock, and things like that. So basically we're using old corrugated containers to make new corrugated containers. We can also use mixed waste. It's a lower cost input to our system, and we can use that if we have lower quality applications. And especially for things like folding board, which we'll mention later. Newsprint, if we want to make newsprint, typically newsprint and other types of paper that contain groundwood that are used for temporary purposes, those are made from old newspaper and magazines, and they're de-inked. And then we've got tissue. Well, tissue can be made mainly from bleached printing and writing wastes and then converted into the tissue. And then we can also use that printing and writing waste, we can use wood-containing papers in that if we have lower quality applications, or if we have a robust system that can handle wood-containing papers. And then finally, printing and writing materials. We make those, things like ledger, copy paper. We make that out of bleach printing and writing wastes. Okay? We just convert them and de-ink them into new printing and writing grades. So just as I just kind of want to review this graph, it's more or less the input material rather than the products. But you can see here that OCC recycling at around 23 million tons per 23 million tons per year in the United States is the category of recovered paper that's recycled the highest. So that's that blue bar. ONP at around 10 million, printing and writing around 12, and office around 5 million. So what you see is that OCC and ONP are largely recycled, as are printing and writing, but OCC dominates. OCC is recovered. The recovery rate, 75%. Newsprint, 72% about. Printing and writing, around 40, and office waste, around 48 or so. So you can see that OCC and ONP are mature industries in which we're recovering a lot of the material. Printing and writing and office are less mature and much more difficult to recycle. So our recovery rates are much lower on those. Okay, so where does the old corrugated containers go? And this just kind of reviews what we said about what we're making our products out of. The OCC, or old corrugated containers, most of it, 62% of it, goes to container board. Okay? And then of the other material, a very small fraction goes to tissue. And then packaging, industrial converting, some goes recycled paperboard, that's folding board. A good chunk goes there. So basically, old corrugated containers are going back into new container board. Where are the old newspapers going? A good chunk of the old newspapers are going to make newsprint. So 30% of the old newspapers are going to make newsprint. Actually, domestically in the United States. We also have exports. And I would say a majority of this is also going into newsprint. But you can also see that some goes into tissue, some goes into recycled paperboard. So newsprint is a very cheap alternative material for these two applications. This category right here at 18% is molded products, and then a small amount goes to printing and writing. Okay, where do printing and writing papers go? Basically, we're putting some into printing and writing at 11%. Some's going into tissue at 22%. Some's going into the recycled paperboard, that multi-cylinder, very inexpensive folding box board. And then we're exporting, at least in the United States, 38%. And I would imagine that that split is similar to the split here. Okay. All right, so now what I want to do is I'm going to go over a newsprint de-inking mill. And we're going to go over this actual newsprint de-inking mill in detail. We're going to look and see all the different factors that come into play in the process, what the unit operations are doing, how the water is being handled. We're going to go into that in much more detail than some of the other systems. So let's go ahead. Okay, so this first graph, I decided I would use our scanner, our paper projector, and let me just go ahead and find that. Okay. Here we go. All right, so this will start off our system. First, let me actually talk about this. We're making recycled newsprint, okay, and we may have like a batch or continuous tub or drum pulper. And our strategy is going to be, first we're going to remove coarse contaminants, then we're going to remove smaller contaminants, do de-inking, and then third we're going to disperse unremoved contaminants, and we're going to maybe try and even remove those too. We may use bleaching to increase our brightness, and then problems with stickies might be an issue, especially if we add old magazine. And I should mention that usually there's blends of newsprint and old magazine. And the old magazine at 20% of the total furnish is used for two reasons. The fibers tend to be a little bit brighter. There's more chemically bleached pulp in there, so you get brighter fibers. The ink comes off easily because a lot of that magazine is coated, so the ink comes off. And there's a lot of filler, and that filler can help in flotation. It's usually used as a carrier to enhance the flotation efficiency. So let's go ahead and look at our process here. So this is just one example of a newsprint production facility. So we're going to start off with our waste paper, and we're going to pulp, and we're going to get some very large rejects, so like wires and plastic bottles and things like that. Then we'll go to high density cleaning. Here we're removing things like staples, metals, glass, paper clips, very larger items. Then we're going to go to pre-screening holes. And in this case, we're going to use 0.05 to 0.09 inch holes. And we're going to, again, remove rejects, coarse rejects, little pieces of plastic, things like that. Then we're going to go into our flotation de-inking, where we're going to be removing ink and fillers and fines. And so this is actually going to be part of our sludge system. Everything above this is going to be part of our reject system. So this would be sludge. And then we're going to do some forward cleaning. We're going to remove sand and grit. We're going to remove inks actually there too. All right, and then we're going to do our cleaning. And then screening comes next. Fine screening. We've got 6 1/1000ths of an inch slot, and we're going to remove very fine contaminants such as small sticky particles. That's really important. Now in this case we're showing washing going on. So we're removing some ink in the washing process. So our wash water is going in over here to a white water system where we'd probably clarify it and then send that water back to the pulper. Then we'll do thickening to 30% and then dispersing. So we might run it through a high consistency disperser and try to break down those visible particles that still remain. So we break them down to subvisible, and that can cause for a brightness reduction. And then we go to high density storage and paper mill. So that's a very simple example of a old newsprint, old magazine recycling process to make new newsprint. And now we're going to try and go over this this kind of system in a lot more detail next on our slides. So we'll come back to our slides, and then we'll go to the next one. So this is actually out of the book Recycled Fiber and De-Inking, the Paper Making Science and Technology series, and co-published by Tappy. So let's kind of go over this, and what we do, we're very fortunate actually that this book was able to get data from one recycle mill and all kinds of different data, consistencies and stickies and ink and brightness. Very nice, complete story here. What you first see here is that the newsprint recycle process that we're going to talk about here is broken up into 3 loops. You got a paper machine loop, a loop 2, and a loop 1. And that's an important way to think about recycling processes. As you see later, we're going to, each one of these loops is going to have its own basically water system, and we're going to think of the process in these loops. All right, so the product we're making is newsprint and improved grades with a basis weight of around 40 to 90 grams per meter squared. And we're using, like I said, newspaper and magazines, typically 80% newspaper, 20% magazines. Our yield's going to be approximately 83%, and that might be data that's actually coming from this particular mill. And we've got some water effluent, 8 liters per kilogram of product. And then finally, our ash, our feed is approximately about 22%, and then our finished paper ash is about 13%. And our finished paper brightness is around 63 to 66% ISO, so typical newsprint. All right, let's go back. Let's kind of just look at our system first before we go into some of the details. Our system's going to start off with a pulper. It could be a drum pulper or a batch pulper. Then we're going to go to the coarse cleaner. So remember that rule I said that we want to remove the large stuff first. Well, that's what the pulper and the coarse cleaner are going to be doing. Coarse cleaner is moving big pieces of glass and plastic. Then we've got a medium consistency screening with holes, again to remove some of the bigger stuff. And then finally we're going to go to flotation, where we're removing our ink, trying to get a higher brightness, lower ink content sheet. Then we're going to go to our forward cleaners, where we're going to be removing sand and grit. Low consistency screening, we'll use a slot here, perhaps a fine slot, and we will try to remove stickies. At that point, what we're going to do is we're going to use a disc filter to increase our consistency, and then followed by a high consistency press. That should get us up to about 30% or so consistency, and what that does is it keeps all the water in loop 1 kind of to itself, and we're only going to loop 2 is mainly solids, okay, or a higher percentage of solids if we were to at that consistency. So at that higher consistency, we got some washing done, a little bit of washing done, but not too much. And then we can do dispersion. And at that high consistency, we talked about bleaching. We talked about if you apply bleach at a higher consistency, you'll get a better response because you've got a higher effective concentration of bleaching chemicals. So in this case, we're going to do oxidative bleaching, something maybe peroxide. Then we're going to do flotation at a lower consistency. This must be done at low consistency. So we do flotation, de-inking again. And that follows that rule that I talked about. We want to repeat inefficient operations. Then we'll go to a disc filter, thicken it up a bit, and then we'll go in the paper machine loop. We'll do, because in this case the reductive bleach is compatible with the paper machine water, we'll go ahead and we'll do our bleaching here, a reductive bleaching, and then a little bit, now we want to do two operations, cleaning and screening, and these two operations right here are used to basically protect the paper machine. So we'll try and remove sand and grit and maybe those kind of materials here, and then the low consistency screening will try to remove any residual stickies or contaminants that might foul our paper machine. So that's our system, and we've got our three sections. So we'll jump right into it and look at some of the data. And this is pretty unique data in that we've got a nice complete set here. Okay, so for loop 1, we're going to start to pulp at maybe, let's say, 15% consistency. And then we're going to go ahead, and what you notice is the consistency will decrease, decrease, decrease. And you see that we're adding water here. And you see for screening, flotation, cleaning, and then fine screening, we need to have low consistencies. We're doing flotation at 1.2% consistency, the cleaning at 0.9% consistency, and the screening at 0.8% consistency. So we've done all these three operations together because we're at a low consistency state, and that's useful for all three of these. So we don't want to be thickening and then diluting and thickening and diluting if we don't have to. Now at that point, after we do our low consistency screening, we are going to start to thicken. Our disc filter will get us up to about 10% consistency. Our press will get us to 30%. And then we're going to do our dispersion, and we'll do our bleaching at that higher consistency where dispersion and bleaching are more effective. Then we're going to go ahead and we'll dilute now down to 1.2% so we can do our flotation, which depends on lower consistency. And then we'll thicken up a little bit, and then we'll go and do our reductive bleaching. And then finally we're going to dilute down to the 0.8 consistency, which is the head box. So you see that we're thickening in loop 1, and we're trying to just pass solids through to loop 2. And in loop 2, we're going to thicken again, and then pass mainly solids to the paper machine loop. And then in our paper machine loop, this is where we're going to, we really need things clean and the best that we can so that we make the best product. Okay. Now we can kind of look at the ash content as we go through this mill. The ash content in the pulper is about 20%. That's the level there. And then you see that the ash content starts increasing. Okay, so the ash content, that's the percent ash of total solids, starts increasing. Now, why would it increase? What's happening here? Actually, we're recirculating water, and that water that we're recirculating has ash in itself. So that's how it can increase. And then as we go to flotation, the flotation drops our ash from 23% down to 18%. Why? Because flotation can remove some of that ash and as a sludge that goes with the ink. Then we have our ash at 18%, and then we wash out some of our ash with our disc filter. So our washing process can remove some of our small ash, and so now we're down to here. All right, now our ash levels are lower. We're actually using cleaner water in loop 2, so our ash levels are lower, except we go up in our ash content in flotation. And again, that's because we had to do a lot of dilution, and that dilution water has some ash in it. And the ash is actually good for flotation. Remember, we talked about that piggybacking, where the ash particles are actually used to kind of agglomerate ink particles. And then a disc filter lowers our ash again. And then finally we're in the we're bleaching at a lower ash level, And then finally, when we get to our paper machine, we're going to have, we're recycling so much water here that paper machine loop is kind of like a washer, and the ash is actually accumulating in this water system, and that's why we have higher ash values near the in the paper machine operations. Now our final product is only 13%. So what you see is that there's a load of ash that's running around the system in our cleaner, screening, and paper machine. Okay, and that ash actually just kind of accumulates there and gets to a steady state value, and we try to get rid of some of it. And our final paper product's around 13% ash, which is important because the ash is going to have impacts on our optical, on our strength, and on our surface qualities. Okay, now we all know that stickies is a big issue, and this graph right here shows us where we're getting rid of most of our macro stickies. So our macro stickies are our larger stickies, and the black bars indicate the inlet, and the white bars indicate the outlet of stickies in each stream. So you can see right here for our medium consistency screening with holes, we're going to go from about 5,000 parts per million to about 2,900 parts per million. So a lot of stickies removal in the screen. Then we go to flotation, and we get some stickies removal of the macro stickies. Some of the stickies are lightweight and they'll tend to float, but just a smaller percentage. And then we'll go to our cleaner. This one's removing sand, and as you see, the inlet and the inlet is this level, and the outlet is also basically that level. So there's no reduction in the forward cleaners. Then we get to the fine screens, and the fine screens do a nice job. We're lowering, and the stickies that are removed in the fine screens are the smaller ones, the ones that are much harder to get rid of. And we're removing them from a level of about 2,300 ppm, millimeters per kilogram squared, excuse me, down to about 800 or so. So we get a large reduction in our fine screening, and that's what most people have come to realize, that screening is our best friend in the fight against stickies. And then we're going to do a little bit, not much changes here with the disc filter and the high consistency press, so it's still around here. In fact, we may introduce some more stickies. I'm not sure why that would go up, but maybe they're just a little bit more detectable. Okay, then we're going to go to dispersion in loop 2, and dispersion is going to be able to cut some of those macro stickies. Remember, these are macro stickies or large stickies, so we get about a 50% reduction there. And then bleaching has no impact, and then we do some flotation, and we're getting rid of about 50% of that. And one of the reasons is because we've done our dispersion, and that dispersion basically has made those sticky particles smaller, and the smaller particles are easier to float out of our system here. So now we're down to around, I don't know, 100 or 200 millimeters squared per kilogram. And then the disc filter has no effect, and then we basically have a very low level, but we have a measurable level in our paper machine loop, so we still have to deal with these stickies in our paper machine loop. Just as an example of how hard it is to get rid of stickies. All right, now when we sell newsprint, we want it to be bright, so we're interested in the dirt and the brightness, and this shows the dirt. And the graph is showing here that flotation 1 is the main operation that's going to remove a considerable amount of ink. Okay, we do have this drop in contaminant level here, but that's more of the gross, large material, flakes and things like that. But then it's our flotation step that really helps us go from 1500 to 480. And then our dirt content just stays about, takes a little drop with our cleaners and screens, and then it goes like this, and then when we disperse, we drop it down again. So our dirt speck area, our large ink speck area, decreases here because the dispersion breaks that up mechanically. And then this little bump right here is the flotation 2. And that doesn't look like a big one, but actually going from, let's say, 200 to 100 ppm is important for our brightness. And then we're going to just kind of keep going like this, and we get a final dirt speck area of 100 ppm, which is not that clean compared to like printing and writing grades. Okay, then the next thing we can look at is our brightness. Very important. Selling a paper newsprint on brightness. First jump, we go from about 46% ISO brightness to about 57% in our first flotation step. And then we just kind of go along the way. Our brightness goes up a little bit when we do our disc filtering and high consistency pressing. So we're kind of a little watering there, but not too much. And then we're going to do our dispersion. Actually, our brightness can go down in dispersion if we take a lot of large particles and break them down to subvisible, then we can get a lower brightness. But basically, as we go ahead and do our bleaching, we're going to go from about 58, 59. We're going to get a couple points brightness increase when we do our oxidative bleaching. And then flotation 2 unit operation, we're going to get another 3 points of brightness because of our flotation. So this second flotation, because we've broken up those large particles, and we've already removed some of the large particles in our first flotation, that flotation 2 step, as you recall, when we go to here, we didn't really see much of a dirt change, right? But really the importance of that second flotation step is to increase the brightness, okay? And we're getting a good increase in brightness right here. And then finally, once we get to our paper machine loop, we get another step increase in brightness because of our reductive bleaching operation. Okay, another important thing to talk about is the way we handle the water. And I told you we broke the mill down into 3 sections. And one of the reasons why is because we want to keep the water in each section to itself mainly, and then pass dirtier water in the direction of the pulper. So we'll start off here in the paper machine loop and we'll work our way backward. Let's talk about the water. Water that comes off the paper machine, you know there will always be some excess water off a paper machine. Well, first of all, I should say, we're going to add fresh water to the paper machine. That's our cleanest water, and that's near our product, so we're using our cleanest water closest to our final product production to keep our product clean. Well, all right, so the water here actually is relatively clean, and it's going to go to a dissolved air flotation clarifier. That dissolved air flotation clarifier can work in 2 ways. In one sense, a lot of the times these DAFs that are on a paper machine are used as a save-all. And so the solids that we get here, actually they're pretty clean and we can put them back into the product. So we do that. And then the other thing is we reuse the water. So some of that water goes here. But we also take some of that, all that excess water, which is relatively clean. So that excess water is actually going to go into loop 2, actually into the flotation step. All right, so we're using our water from our paper machine. That's going to be the cleanest in loop 2, and that's going to go into our flotation. And so you see we're going to add that water in this direction. The pulp's going that direction, the water's going in this direction. So it's countercurrent pulp and water flow. All right. So we're going to get some water from our loop 2, and that water is going to come through here, down here. That water is going to be on our disc filter, and that water will go to our DAF2. That DAF2, that sludge will probably be treated and sent for disposal. And then the water actually is going to go in this direction from the DAF2, and that's going to go actually and used as dilution water for our pulper. So our pulper right here is going to accept that DAF2 water. So you see that the DAF2, the water from loop 2, actually is going in this direction towards the pulper. So we get that countercurrent flow of the water getting dirtier and dirtier and dirtier going right to left, and the pulp getting cleaner and cleaner and cleaner going left to right. All right, so what actually happens in loop 1 and loop 2 here, and actually in the paper machine, let's talk about the 2 kinds of rejects we get. Early on in our process, we're getting rejects from the pulper, from the cleaner, high-density cleaner, and the medium consistency screens. So these are large chunks of metals and foils and plastics, and they go to a reject system right here. This reject system, because these materials are pretty free-draining, some water will be drained off, and that water will go to the DAF3, and that will be pretty dirty water because it's coming from the dirtiest area of our paper recycle mill. And then the rejects will be disposed of. Then the other kind of waste we get is our sludge. These are finer, much more organic material, a lot more fines and fibers in here. And we're getting them from the flotation, from the cleaners, from the screens. And then we're also getting some from this flotation. We're getting it from this cleaner and this screen. So all those flows are going to come down here. It's going to go to our sludge treatment plant. We talked about how sludge is thickened, so we'll use a thickener and then maybe a screw press or a table press. And so that sludge, actually the solids are going to go here and they'll be disposed of. And then the water is going to go to DAF3. Now DAF3 has got the dirtiest water possible because it's got like all the sludge from the de-inking processes, flotation. And we're going to have some effluent. There's got to be some release of material here in this effluent right here. Now if we don't have that, what we'll have is we'll have a buildup of we'll have a buildup of soluble and colloidal particles in our system that we won't get rid of, and eventually that will just, if we have such foul water, we won't be able to do de-inking. So we're going to drop some effluent, and this effluent basically has to balance this fresh water plus other losses that we have in our system. And then the DAF3, the water that we produce here, that clarified water is going to go back to the pulper. So this pulper is going to use the dirtiest water to pulp up. And so again, the important thing is our water is going this way, getting dirtier and dirtier and dirtier, and our pulp's going this way, getting cleaner and cleaner and cleaner. So that's our water and waste systems there. All right, and then this just basically kind of describes some of the rejects we're getting. For those coarse rejects that we were talking about, flakes, plastics, woods, wires and things. And then we'll also get small heavy particles like sand, staples, and glass. And these would be pretty easy draining material. And then we get our fine rejects like plastics and flakes. So all three of these are going to be our rejects. And then our sludges are coming from our flotation, fine forward cleaner, fine screens, and screens and cleaners in the paper machine section. So here's our sludge. Here's our easier draining rejects. Okay, so we really probe deeply on that newsprint de-inking mill. That's some real good data. It gives you a good flavor on all the different things we have to do. We have to look at brightness, we have to look at dirt, we've got to look at fillers, we've got to look at how we're managing our water, how our fiber is flowing, how our operations are set up. So we went into strong detail in that. Now we're going to kind of know those concepts and see how they might apply to other ones, but we're not going to go into them in as much detail for these next
We've
systems.
got about 18 minutes on the tape.
Thank you. Thank you. So for de-inking of printing grades and printing and writing, we're going to be taking office waste, printing grades, and recycling them into new printing and writing grades. So couple things to talk about. We may use mixed or sorted waste, and there's a cost trade-off there. The mixed waste is going to be harder to recycle, but it's going to be cheaper. And then our strategy for this process, and I'll show it to you on the projector in a second. We're going to first remove coarse contaminants, then we're going to remove smaller contaminants in de-inking, then we're going to disperse unremoved contaminants, and then we're going to bleach to higher brightness. And this is a very complex process that's very difficult to control and run without trouble. Okay, so here we are. This is just one example. So we're going to have our pulping system, and then we're going to remove large rejects there. Then we're going to have high density cleaner. We're removing glass and metals and wires. Pre-screening holes, so we're going to remove a lot more. This pre-screening here tries to protect the fine screens, because the fine screens at 6/1000ths of an inch slot, those can get plugged very easily. So this protects this. So we're getting rid of the large stuff first. And then this one with the 6/1000ths of an inch slot is going to remove stickies and flakes. So we'll get rid of those. And then we're going to do forward cleaning, get rid of some dirt, maybe a little bit of ink. Then we're going to do washing, where we're removing some of the ink particles. Then actually in this case we're thickening to about, it says 28% consistency. Then we're going to be doing dispersing or kneading. At that higher consistency, again, we're going to add some bleach, and we're going to go to our bleach tower and do bleaching. At that point, we're going to do flotation to remove ink particles from our system. Then we're going to do reverse cleaners, so these are removing waxes and stickies. Forward cleaners to remove large ink and some sand. Finally, some thickening, and we'll store the stock, and then we'll send it off to the paper mill. So you can see there's a lot of different operations, and this is a simplified schematic of what's going on here. So if we go back to our slides, again, we can think of the high-grade printing and writing grades. We can break the system up into loops. So we've got a paper machine loop, we've got a loop 2 and a loop 1 here. For our paper machine loop, again, because we're very interested in the final brightness and cleanliness of our product, we're going to use all our fresh water in the paper machine loop. Okay? And then that water will be recycled to loop 2 and loop 1. Okay? And then again, we're going to have the dissolved air flotation clarifier that's actually sending water back to loop 2, and then loop 2, the DAF2, is sending water back to loop 1. Loop 1 has a dedicated DAF itself that's going to try to clean water in here, and then we're also going to have a DAF for some of our reject and sludge, the water that comes off those processes. So in this case, we've got a high consistency pulper, we've got a coarse cleaner, a medium consistency screen. So we're getting rid of some of our real big stuff here. Then we've got a medium consistency screen now with slots, flotation process, forward cleaners, low consistency, slotted screen, and then washer. So you can see all these 4 operations right here depend on inputs that are low consistency, so we keep those together. A press, that isolates water from loop 1 and water from loop 2. In loop 2, we're going to do dispersion. At the higher consistency, we're going to do oxidation bleaching, because that works better at the high consistency. Then flotation to remove ink. And then a disc filter and press, again, to isolate the water from our next step. It will also, the higher consistency is going to help us with our reductive bleaching. And then we're going to maybe do a little refining, and then cleaning and screening. Now these are just polishing steps in order to protect our paper machine. And there we have our system. So you can see there's a lot of operations. We've got to make it clean. We've got to make it colorless. We've got to make it, well, white, I should say. We've got to make it, the final product, have good surface properties and good for printing and writing. So there's a lot of things that we have to do there. All right, now let's go to the production of tissue grades, another white grade, I'll call it. For de-inking, printing and writing grades for tissues, we can use sorted or non-sorted waste to make tissue, okay? And we've got the same trade-offs as we had before. Cheaper stuff is non-sorted, but you're going to have to deal more with variability of incoming materials. For tissue making, our filler level needs to be low. Remember that I said that that creping process where you have this metal blade, creping blade, scraping this metal drum and making those crepes in the tissue, that gets, there's a problem if you have filler there. It will abrade the blade. So we've got to get our filler level down to 1 to 1.5% of our solids. Our yield can be low. Low is 60% because our incoming waste, like mixed office waste, has got a lot of filler in it. We can also, depends on high quality or low quality tissue. We use low quality tissue here at NC State. The brightness and dirt count may also be important. So depending on who you're selling it to, that's important. Lower grade tissues are going to obviously have not as many unit operations. So they might omit one stage of cleaning, bleaching, and washing. May also omit flotation. So here's an example. We've got our recovered paper here. We're using a high consistency pulper, high density cleaning, glass and foils, coarse screening with holes. Then we're going to do forward cleaning and fine screening. So forward cleaning is getting rid of sand, grit, chips. Fine screening is getting rid of the adhesive. Then finally we're going to start to do washing. We're going to do washing to remove a lot of filler, thickening. We're going to do some dispersion in this case, and then bleaching at that higher consistency. Flotation, that's going to remove ink and also filler. We're going to do a second stage of washing to get rid of even more filler. Some cleaning and fine screening, and then it's stored for the paper machine. Okay, now just as a couple examples, we can kind of compare low versus high-grade tissue making. In this case, again, for making low-grade tissue, we've got 3 water loops. We're going to keep them separate. We're going to introduce the fresh water in the paper machine loop. For the paper, and we're going to use our DAF here, or dissolved air flotation, to clean up some of the water, send it to loop 2, and then from loop 2, we're going to send it to loop 1. All right, and what you notice here is we've got pulping, cleaning, screening, and then pressing. The pressing is going to get us to higher consistency, so we can do dispersion, flotation, washing. Then we're going to have only one bleaching operation. So remember that. For low-grade tissue, we get away with one or none, really. And then we'll do cleaning and screening to protect our paper machine, so low-grade tissue. Now, in contrast, if we were trying to make high-grade tissue wood-free, we're going to add a couple operations. So one of the operations we'll add is right here in loop 2. We're going to have oxidative bleaching also in loop 2. So we have oxidative and reductive bleaching both in loop 2. So we're going to get to a higher brightness there. And if we go back and notice, in this case we have no flotation and one washing step. For higher grade, we're going to have 2 washing steps. We're going to have one washing step in loop 1, another washing step in loop 2. And then we also have added flotation to remove inks. So that's the adjustment that we have to make higher grade tissue. Okay, now the lower grade tissue that has wood-containing material in it, that wood-containing material usually indicates to us that we have newsprint. And newsprint means we have more ink and more dispersible ink. And so to deal with that more dispersible ink, what we've got to do is we've got to have everything that the non-wood containing, oh, and this is high-grade tissue. I apologize. This should be high-grade tissue, wood-containing. So for the high-grade tissue wood-containing, we're going to add one thing compared to the non-wood containing, and that's going to be flotation 1. So not only do we've got to have 2 flotation steps, and we're going to have 2 washing steps. So this is going to actually try to get rid of a lot of the ink, and it's going to be a lower yield process. Okay, so that's basically tissue recycling, and remember that's high grade tissue, wood containing.
Richard, I got about 8 minutes left. Should we do a transition, go to
No,
another tape?
I think we're fine. Thank you. All right, now the last topic is the production of packaging grades. So these are your brown grades. The first system is the simplest system. This is going to be a very high yield, and this might be used in a filler system for boxboard mills or something. It's easy to operate, low capital, very high yields. If you look at this simple system, there's no capability to remove contaminants. So the contaminants have to be removed before pulping. So you might have to use some kind of pre-consumer waste. The product quality is simply a function of the input furnace. So in some cases we're going to use clean corrugated, pulp it up, store it, put it on the paper machine. Very simple, very high yield. All right, now we can start talking about a crude cleaning system for packaging products. So this is used to produce liner, medium, or tube stock. Simple, high yields, and the ability to remove coarse contaminants only. And it can be often used with a continuous pulper. So let's look at that. Okay. So this operation, we're going to take relatively clean corrugated. We'll pulp it with a continuous pulper. High density cleaning to remove plastics, films, foils. Coarse screening with holes, 0.06 to 0.1 inch diameter. Then we're going to thicken, store, and write onto the paper machine. So it's a very simple process, crude cleaning system for making high yield packaging. Okay. All right, now if we're making multi-ply board packaging product, and I want to just talk about this for a second, that's the folding box board. So it's like shoe boxes or boxes that you put food in when you're taking them out from a restaurant. These things have to be stiff, they have to have ply bond strength. So the way we make these thick products is that we use multiple cylinders and we put down layers of this material, and that helps us make our thick product, and also helps us kind of partition good and bad fiber. Basically, this top liner right here is the highest quality. So that could be actually bleached virgin or de-inked pulp, and that's going to be clean, and the consumer will see that. And then the underliner here is also going to be kind of bright. It'll be a lower quality grade, but it will help us in our brightness of our outer liner. Then this liner right here is called the filler, and that's just the waste junk. That can be the dirtiest, junkiest stuff that you can find. So that's our filler. And then finally we've got our back liner, so that would be the inside of the box, and that has to be a little bit cleaner, and it's got to be a little bit stronger. So for that back liner, we're going to use maybe a recycled kraft unbleached pulp. Okay, so we've got this interesting construction. We're using cleaner stuff on the top here. So 1 is cleanest, and 2 is second cleanest, 3 is third cleanest, and 4 is fourth cleanest. So we're kind of constructing a nice product here. Another thing to mention is that the cleanest water is used in the top liner, and then that water goes to the second cleanest, and that water goes to the third, and that water goes to the fourth. All right, so if we look at OCC recycling for higher grades, we're going to use this to make liner board or medium, and we're going to have often a continuous pulper, and we're going to, again, remove coarse contaminants, then remove smaller contaminants, then remove dispersed, unremoved contaminants. So let's take a look at that. So here on our projector is we'll have our paper stock coming in. We'll pulp with a pulping system, usually low consistency continuous, high density cleaning, coarse screening, dilute. Then we're going to do some cleaning at a lower consistency, screening, light rejects to remove wax and other materials. Then we may do fractionation. I'll talk about that better on the next slide. Thickening, dispersing. So fractionation and dispersion are optional. High density storage, and then off to the paper mill. So you notice that there's no de-inking capability, and we're just trying to get rid of all the stickies and contaminants that are going to hurt our product. So this graph kind of shows you a test liner production. And what you do here is we've got a pulper, and then we have another system to reject some of the large materials. And then we have a disc screen, and that's just a screen, and then that's going to actually send the fibers to a high density cleaner. And then finally we're going to go to a low consistency screening with a slot. And what that will do is it'll separate 2 streams. We're going to have our cleaner, our accepts from this screening, go into our top liner. Our rejects that are going to be dirtier are going to go into our back liner. So our top liner is what people are going to see the outside of the box. That top liner will be thickened and then sent for screening and on to the paper machine. The back liner is actually going to have to go through a couple more screening stages, and then thickened, maybe even refined, and then to another screen, and then that will be used in our paper machine. So you see we're using this first screening operation to separate top liner from back liner. What this also will do is we'll get finer, shorter fibers in our top liner, which will help us in smoothness. Our back liner will have the longer, coarser fibers, which we potentially can refine and improve our product. And what this shows right here are stickies contents. And you see the stickies contents decrease. And then finally, when we get to the separation where we screen right here, our top liner has a very small amount, only 800 millimeters squared per kilogram of stickies here. And then our bottom back liner has higher, and that's why we have to clean, and we eventually get down to 1,600 millimeters squared per kilogram of stickies. Okay? All right, so this is my last slide. We've kind of gone over all the different types of systems, and you can see some are very simple, some are very difficult. We've broken them up into white and brown. And so our first learning objective was appreciate the strategies involved in designing a recycle process. And what we did was we found out that, well, yes, for white cases we need cleanliness and optical are very important. For brown we need strength and we need some cleanliness to run our board. Our production rate and our yield are also important, and all these impact profit, safety, and environmental. We also want to recognize the relative number and types of sub-operations in each recycle process. So it depends on the product we're making and the incoming raw material is basically what it boils down to. So we need different operations to deal with inks, large junk, stickies, fillers, and brightness. And so tissue operations are going to have different processes than linerboard. And then finally, we need to understand that reject, sludge, and water management is important in our recycle system. So we're using countercurrent flow of water and pulp to improve quality. We're thickening to isolate water loops. We're doing unit operations that are low consistency together. Large rejects are easily drained, and then sludges are dewatered and pressed. And that kind of concludes our course. I hope you got a good overview of the details of paper recycling, and we kind of put it together today. And as you can see, paper recycling is a complex, interesting, fascinating topic. And there's lots to be learned, and there's more research to be done, and lots of improvements that we can make. Thank you, and that concludes the lecture.